My name is Vladik, and actually, I want to ask your permission to skip this whole boring part of speaking about myself and instead go straight to the topic that really want to hear about. Is that okay? Great, cool. So, the topic I want to talk about is messaging. More specifically, the architectural pattern we usually call events. And the thing is, events are everywhere nowadays. We have event-driven architecture, we have event sourcing, and of course we have microservices. Hey, many are calling for integrating them asynchronously through events as the default integration method. But this popularity came with a cost. Somehow many consider events to be some kind of a magic sauce of distributed systems. As if you can take a monolith, pour some events over it, and boom, you've got yourself microservices, domain-driven design, and overall modern distributed architecture. And of course, that's not true, right? This pattern is not some kind of magic, but it's just a tool. And as any tool, you can use it to create some great stuff, but if you're going to misuse or abuse it, you're going to pay a hell of a price for doing that. And fortunately or unfortunately, I have experience of doing both, misusing events and abusing them. And in the next 40 minutes, I will share my experience. I will show you the troubles I've got myself into, how we got out of those troubles, and most importantly, what we had learned along the way from that experience. But before we get to those war stories, I want to start from the basics. I want to make sure that we are all on the same page on what is software architecture, what are its goals, and what exactly are those events that we are talking about. The war stories that I will share later are going to be based heavily on this theoretical part. So, what is software architecture? When pondering this question, usually this quote comes to mind. Architecture is about the important stuff, whatever that is. I guess no one would argue that it isn't important, right? Robust software architecture is crucial not only for the success of the system that we are implementing, but in many cases of the whole organization that software is supposed to serve. For example, in my previous workplace, I was the first employee. So back then, we had to make a lot of architectural decisions. We had to decide, for example, whether to use self-managed servers or go to the cloud. And 9 years ago, it wasn't a trivial decision. We had to choose languages, frameworks, libraries, and of course, we had to align the system's architecture with its business domain, which was quite puzzling back then. And all these decisions were hard and risky. Correct one would move the business forward, while a wrong decision would make the system way harder to implement and to maintain, both in the short and in the long terms. So architectural decisions are not only important, but they're also hard and complex. Therefore, in my opinion, the goal of software architecture is to manage complexity of software systems. And usually we manage this complexity by dividing systems into components, into sets of interconnected components. We usually call them modules. Those modules can appear at different levels. They can be methods, classes, namespaces, services, even whole systems. But at whatever level they are, the underlying idea and the underlying principles are still the same. Proper modules make it easier to reason about the system as a whole and about each of its components individually. On the architectural level, modularity reduces risk of those design decisions that we are making. It limits the scope of each decision to the scope of the module itself. For example, if you have a service which uses a relational database, but for some reason we have to migrate it to, a document store, that change is going to affect that specific module only and not the whole system. Put differently, modularity allows us to divide the complexity of a system into two types. local complexity and global complexity. So local complexity is a complexity of each individual component. And the easiest way to demonstrate this notion is a simple heuristic I like to use to evaluate it. So let's say we have a module, and we have to ask how easy or how hard would it be to introduce a junior team member? How hard would it be for them to understand what this module is supposed to do, what problem does it solve, and how is it implemented? For example, in our system, we had a module which was in charge of calculating commissions for sales agents. All of its public API resembled a coherent set of methods in one way or another related to those commissions. Now, because its business domain was quite limited, its implementation was quite predictable. It was easy to find a way around there. On the other hand, at one point we had a module which was in charge of managing and publishing advertising campaigns, managing creative catalog, and even taking care of the company's finances, billing. At that case, forget about the junior developer. Some points of time, I had no idea what was going on there. So that second component has a much higher local complexity. The second type of systems complexity is global complexity. And this one is defined by the level of interconnectedness between the system's components. With low interconnectedness, it's easier to understand what role each component plays in the system. And it's also easier to evolve those components, since change in one of them will have a much lower impact on the rest of the system. And here we have an example of a system. And it's hard to tell objectively whether it has a high or low global complexity. But if we compare this one to this system, that it's evident that here we have a higher global complexity. It's the same number of components, but they're much more interconnected. There are much more dependencies and coupling between them. So this second system has a higher global complexity. So proper components boundaries reduce complexity of the system and make it more adaptable to future requirements and changes. And that makes the process of defining components boundaries a key architectural decision. So if we go back to the question of what is software architecture, in my opinion, Ruth Malan gave a crystal clear answer. She said that it's inherently about boundaries. What's in, what's out, what spans, and what moves between. Boundaries reshape what is outside just as they shape what is inside. So systems design is about drawing boundaries between components. And speaking of what moves between those boundaries, let's talk about the pattern we often use for decoupling components of a system, events. And the idea behind this pattern is fairly simple. An event is a message which is used as a contract for integrating systems. Usually that's what a typical message looks like. We have some metadata that describe the event, who published it, when, why, etc. And we have the payload which carries the message itself. That's the information we want to communicate to external systems. Now, according to the contents of that payload, we can categorize events into three types. And I took those definitions from Martin Fowler's article called What You Mean by Event-Driven. So the first one is what Martin Fowler calls event notification. Such event is used to notify that something important has happened, but it contains minimal information on the nature of the change. If a subscriber needs more data, it can explicitly query the source system to get further information. In some sense, event notification is like this weird thing right here. Do you know what this is? Pager, right. So that's the idea. You get this message saying, hey, something is going on, But if you need more information, you have to call this number. That's the idea of event notification. The next type is what Martin Fowler calls event carried state transfer. And here the source system uses events to notify its subscribers about changes in that system's internal state, its data. And let's say we have this record of a customer. Let's say we have a service which manages customers. And this service is interested in publishing events which will describe changes in the data of the customers. It can do it in two ways. First, it can publish a complete snapshot of each customer. So if some field changed, we just pack it as a JSON and publish it to the message bus. There you've got it, event carried state transfer. Of course, if that customer has hundreds of fields, we can optimize it and we can just publish the fields that were actually changed. So only if two fields were changed, we'll just publish them. Either way, all data published by such events is sufficient for the subscribers to hold a local cache of that service's data and work with it. They don't have to query the publisher for additional information, like in the case of event notification, right? And the final type is the events used in domain-driven design or for event sourcing. Usually we call them domain events. And they are somewhere in between those previous two types. As event notification, they notify that something important has happened, but they also carry enough data to describe what actually happened. This data, however, should be modeled as close as possible to the business domain and not some particular state representation, as in the case of events for carrying changes in state. As Marian Duncan-Jones says here, stateless as domain event should be stateless as regards to entity to which the event occurred. In other words, money deposited event holds no data on the account balance. So in this example, account balance is the state. We are not publishing it. It's not a part of the business domain. On the other hand, we do have to specify the amount of money. We do have to specify who deposited the money and to which account, all that stuff which describes what just happened in the business domain. So those are the three types of events. And to demonstrate it, I will use this example. My friend from Israel, Ora Egozi, she came up with this example. I really like it. So let's say for a notification event, we can have an event which says marriage. Well, we don't know who married whom and where and when. We have to call the external system to get that information. So that's notification event. On the other hand, we have this personal details changed. And here we can see that a person's last name was changed. We can assume it was because of a marriage or, I don't know, divorce, or they just decided to change their last name. Who knows? But we do get this state, the current state of that person. So that event carried state transfer. And finally, as a domain event, we can have person got married. Here we have an ID of the person who got married. We have the partner ID. We can have a flag which says whether that person assumed the partner's last name. It will be true or false. But we don't hold the current last name. That would be a state projection. That belongs to the second type. Now, it's crucial to choose the correct event type for a specific task. Events that are going through the boundaries of those services that we are implementing, and they are inherent part of those boundaries. And if you saw in the previous part, boundaries are a crucial architectural decision. So if you choose correct type of events for the task, great. We will get a more decoupled system. But if you are making a mistake here, it can lead us to accidental complexities and even the dreaded distributed monolith. And to demonstrate it, I want to share some war and horror stories from my experience at a company called Internovus. At Internovus, our goal was to allow companies that are producing products or services to outsource their marketing-related chores. So we'll come up with marketing strategies, we would create creative materials, we would publish them as advertising campaigns, aggregate leads, and eventually we'll call those leads to sell the products. Pretty complex and wide business domain. And as it usually happens, initially we try to implement this whole thing as one huge monolith. Now, complexity-wise, the system had very low global complexity. Because, hey, you have only one component. It cannot be coupled to itself, so the global complexity was minimal. On the other hand, the local complexity of that component was huge. Everything was implemented in it. Now, unsurprisingly, after some time, this design started breaking under its own weight. This code base became slow, hard to test, and overall, the development process became unpredictable. So we decided to break this monolith into two subsystems. We called it marketing and CRM. That's what it looked like. Marketing system was in charge of collecting and publishing marketing events. For example, impression, click, submitted lead, etc. And it was kind of stupid. It didn't really do anything with those events apart from publishing them to the subscribers. Those subscribers, on the other hand, they were free to do whatever they want with those events. However, as time passed, we noticed that all those subscribers did exactly the same thing. They transformed those marketing events into exactly the same stage representation. Now, it's important to point out that this wasn't a mere projection, but it calculated different metrics for each event. It didn't just, transform the model into something else, just moving those fields around. Instead, it had some complex business logic, which calculated business values. For example, is this event coming from a new lead or an existing customer? If it's a new lead, then what was the cost of gaining it? If that's a customer, an existing one, then what's the projected lifetime value of that customer, etc., etc. And there were many such calculations, and some of them were really complex. Now, not only that they were complex, because that code was duplicated, each time it was modified, we had to modify all those subscribers at the same time. And of course, the hard parts, they had to change the most frequently. And of course, what we are seeing here is a very strong coupling between those subscribers. Also, on the left side here, we were quickly hit in the face by unreliability of the network, because we naively assumed that, the events that we are publishing, they're going to be delivered exactly in the same order as they're published, and also that each event is going to be delivered only once, as if this whole system acted as one big logical transaction. Of course, that wasn't the case. And the moment things didn't go as planned, the same events produced different results for different subscribers. Now, to fix this, we tried to employ some infrastructural black magic, to try to enforce this transaction, this huge distributed transaction. But what we eventually did was just raise the local complexity of those components to the maximum, on top of the huge global complexity that we already had there. So eventually we solved this by refactoring that marketing system into an event sourcing-based system. It would encapsulate all that complex and volatile business logic. And instead of publishing mere notification events, now it emitted more elaborate domain events that described what has actually happened in the business domain. And if we were to look at this from complexity standpoint, this refactoring lowered both the global complexity of the whole system and also the local complexity of its components, because now we removed all that code that was duplicated in all those subscribers. Now, speaking of that CRM system, Originally, we implemented it in, a traditional way. It stored its data in a relational database. Now, after some time, we of course understood that this implementation was limiting us in a number of ways. First, it didn't scale. Second, that relational model was limiting us. It limited the insights that we were able to get from that data. Our business stakeholders wanted more flexible ways of looking at that information. So we decided to refactor the CRM into an event sourcing and CQRS-based system. Our initial CQRS implementation was pretty much by the book. The client would submit a command, its execution would result in new domain events appended to the event store, and it and those domain events were projected into view models. And finally, the command's results were communicated back to the user from the read model. Those are the so-called one-way commands. The information flows only in one direction here. The thing is, there are no commands here. What we are having here on the left side is events masquerading as commands, because a system should be able to refuse execution of a command, and of course to communicate back to the caller the reason why the command was not executed. Was there a technical issue, or maybe the command is invalid? If it's invalid, tell the user how to fix it, right? And in this case, the CRM system's user experience was terrible because of this long feedback loop. So to fix this, we decided to do something risky. I was honestly afraid that some people in the community will be willing to bore me to death, as a traitor, because I said we take this segregation, command query segregation, and we'll relax it. Our commands from now on can return information. For example, if you call the command synchronously, you will get the answer. Did it succeed or did it fail? If it failed, why it failed? And this change dramatically improved the user experience. The users were getting the results of their actions immediately. Moreover, in some cases, instead of querying the projections for the updated view models, we return the updated data as part of the command execution object as well. Because let's say our user updates information about some customer. Hits OK, and then he is presented with stale data, whatever we have in projections. Terrible user experience. So instead, we just return the updated information as part of the command as well. The only limitation, of course, is that this information can only come from a strongly consistent data store, from the event store in our case. Because, again, projections are eventually consistent, we cannot trust them to be refreshed immediately. So whatever we could, we just returned as a part of the command. And again, it improved the user experience of the system. Now the users didn't have to refresh the screen to get the up-to-date information. Now let's speak about those projections. So the CRM system published those domain events as its public API, and it expected other systems to leverage this freedom of generating their own projections. At the beginning, it looked awesome, especially when we compared this to the initial relational database-based design. However, after the CQRS honeymoon period was over, we suddenly realized that 90% of those subscribers projected exactly the same model. And again, as in the case of marketing, this marketing system, this introduced logical coupling. The logic that projected events into a workable state was duplicated in all those subscribing components. Now, not only was it duplicated, but because it held the knowledge of how each domain event affects the state, it was tightly coupled to the CRM's implementation details. The CRM system exposed many different types of events. I think about 200 event types. And all those subscribers had to closely follow changes in the CRM's implementation. And of course, it changed often. And if a new event type was introduced, those subscribers had to reflect that immediately. Why? Because if that new event, a new type of event, somehow affects value of a projected field, then ignoring this new event will result in an inconsistent state. So to sum it up, again, from the complexity standpoint, we have here implementation coupling, we have here logical coupling, and this red thing just screams, simplify me. The system is too complex. So to decouple this mess, we encapsulated that projection logic in the CRM system itself. And instead of exposing hundreds of domain events, it published changes to the projected state through event-carried state transfer. Effectively, the CRM's public API compressed its implementation details, those hundreds of event types, into a much more restricted set of public events that just described, the changes in that projected state. Now, of course, it did raise the local complexity of the CRM system a bit because we introduced new logic, but again, no big deal. That change dramatically improved the global complexity of the whole system. The next story is about a betrayal. So we had this nice microservices-based system, low global complexity and actually low local complexity of the components. And then, because of some new requirements, we had to introduce an additional microservice. That new microservice had to process data from all other services, do some work, make some decisions, and communicate those decisions back to those microservices. Now, what we really have here in the middle is not a microservice, but an architectural Trojan horse, because this thing turned this whole system into a coupled mess. It somehow got coupled to the implementation details of each of those microservices, the original ones. And not only that the horse got coupled to the rest of the system got coupled to the horse's implementation details. So every time one of them had to change, almost always the rest of the services had to change as well. Now, needless to say that in this case, the global complexity just skyrocketed, right? Now, the solution that we used was domain-driven design's anti-corruption layer pattern. We used it, to separate the integration complexity from the business complexity of that new service. The ACL's local complexity was really low. All it had to do is just aggregate data and transform it into another model. The more complex service, the original Trojan horse, ended up encapsulating the complexity of the business domain, but it wasn't so coupled to the rest of the system anymore. So even though its implementation had to change frequently, it didn't really impact the rest of the system. At most, it just impacted that anti-corruption layer in the middle. Now, Nick Tune he speaks about a very similar idea. He just calls it a funnel context. He worked on this idea a bit more, and it's not just an anti-corruption layer as it is described in domain-driven design. So if it sounds useful to you, look for Nick Tune funnel context. Now, the story of the next system started pretty similarly to the previous one. Actually, it was our first stab at implementing a microservices-based system. So how should we design it? And we said, hey, microservices. That micro part is there for a reason. So we'll design those services as small as possible. And of course, we'll integrate them asynchronously through events, mainly through events. Now, look nice initially, as it always happens. But as we implemented more and more features, those services became more and more chatty. Almost each of them at some point needed data from all other services to complete some of its operations. So what started as a decoupled system, it actually ended up being a distributed monolith. Now, of course, to implement it, what did we do? We just poured the magic sauce of distributed systems. We just added more events to publish and to subscribe to. Again, global complexity skyrocketed. Now, the reason for this distributed monolith and the reason for all those events we had to exchange here, it wasn't the real problem. It wasn't the symptom. The symptom of a bad decomposition of a system into components. So what we had to do here is to take a step back and rethink the boundaries. We had to merge some of those services together, some stayed independent, some business functionalities had to be moved across those boundaries, but eventually that refactoring led to a system with much less events flowing between the components. Now, for this last story, I cannot trash talk too much here because I wasn't directly involved in this implementation. So I'll try to watch my language. So about a few years ago, Internobus was merged with another company. And here's what I stumbled upon when we did some architectural reviews. The goal of using events here is to build a distributed, scalable system. Let's see what we really have here. First of all, how this thing works. Users are executing commands. Those commands write some information to a relational database, and then some events are published to a message bus. Subscribers pick up those events from the message bus and do some stuff. Now, the first thing that we have here is transactional coupling between the database and the message bus. Because what will happen if the process will die exactly after committing the database transaction, but just before the event was published to the message bus? The user will get an error, some data will be written, some will be lost, and the end result is data corruption. Also, for all those subscribers, the order of the events was important, but it wasn't enforced by the producer. So that's additional dimension of transactional coupling. Now, let's see what those subscribers are actually doing. The first one is simple. It just picks up those messages and records them to some persistent storage. The second one projects a state representation of that business entity into some in-memory cache, in-memory database. The third one forwards those events to BI for analysis. But first, it enriches all those incoming events with the state from that cache, from the second subscriber. So effectively, these two subscribers, the last two, they are temporally coupled to each other. They should be executed in a specific order, or otherwise the analysis model is going to be enriched with inconsistent state. Now, of course, such orchestration maybe it's possible in some cases, but in our case, we just hoped for the best, and eventually the data just got corrupted. Now, to fix all this mess, what we did is we employed the outbox pattern. We just leveraged the relational database that we already had it there. We just expanded that original transaction to write information to one more table, to outbox. We recorded those events that need to be published. One transaction. Now, the user would get the result of the action once that transaction was completed, and then some relay would pick those messages from the table and publish them to the message bus. Now, That was a very trivial for us to do because again we already had a relational database. It was very easy, to implement a writing to multiple tables in the same transaction. And again, it eliminated all that transactional coupling that we had in that system initially. Now, those are the stories that I wanted to share. Now, let's see what we had learned from that experience. So, first of all, when designing event-driven systems, be pessimistic about everything. Don't naively assume that things will just work. Things won't just work, and trust me on that one, they will fail the most on weekends. That works. Don't test that assumption. And in that last system, what we had here is, I call it optimistic consistency. We were optimistic that things will just work. They didn't. What we got here is eventual data corruption. And that term event-driven architecture, it has this word driven for a reason. Your whole system depends on delivery of those events. So make sure the events are delivered no matter what, even if the system crashes in the middle, or there is a network outage, or the message bus got crazy and delivered the same event 10 times. Your subscribers should be able to handle that situation as well. Next, identify private and public events. Some events, are just implementation details, especially domain events in event sort systems. Now, it might be tempting, to expose them as the public interface, but you do not want external systems to depend on your implementation details, right? You want to be able to change the implementation of your service freely without affecting unrelated external systems. So instead, leverage both public and private events. Private events can be very detailed domain events, and you can have them as many as you need. However, when designing your public APIs, compress those private events into a more restricted set of public events. Those public events should be modeled for the purpose of integrations with external systems. They should be more stable than the implementation details of the service that is publishing them. Also, we saw that there are 3 different types of events. Use them all. Notification events and event-carried state transfer are great for integrating services. Domain events are great for modeling business domains. And of course, instead of blindly integrating microservices asynchronously through events, evaluate their consistency requirements. If you've got 2 services that can settle for eventual consistency, great. Integrate them asynchronously through events. But if one of them expects to read the last write of the second one, maybe it will be easier to just issue a synchronous call and get the most up-to-date data. If you still need push-based integration, then you can publish an event notification, that first type. And then the subscribers will have to explicitly query the source system for the most up-to-date data that they have. And finally, if on the other hand you have 2 services and they share a set of methods that assume some kind of concurrency control between them, in other words, only one of them can change some specific set of data simultaneously, then stop right there. Probably you have your boundaries wrong. You have to align your service boundaries with the boundaries of your business domain. That was the situation in the story of those tiny microservices that I've shown you earlier, right? So those are the 3 lessons that I wanted to share, and I think it's time to wrap this whole thing up. So, quick summary. The goal of software architecture is to manage complexity. We manage complexity of software by using modules. By using modules, we have to deal with global complexity, the level of interconnectedness of the system's components, and local complexities of each components. we have three types of events: notification event, something interesting has happened. We have event carried state transfer for publishing changes in data. And we have domain events, which notify that something interesting has happened in the business domain. And what we had learned from that experience: be pessimistic, assume that things will fail, things won't work, make sure your events are delivered no matter what. Use private and public events to limit the public API of your components, and evaluate consistency requirements to choose the correct way of integrating services. And all this actually brings us back to the topic of what's the goal of software architecture and how modules allow us to manage complexity. So if we get those events wrong, we actually mess those boundaries. And as Ruth Malan said, that's a key architectural decision. And before we go to, I see that we have two questions here. I have a minute for a shameless plug. So first of all, not long ago I published a small book on domain-driven design. The name is simple: What is Domain-Driven Design? It's really a short read, and the goal here is to introduce the basic notion of what is DDD, what are its core principles, and how you can apply some of its components on your brownfield projects, without going crazy with this whole methodology. It's available on O'Reilly's online learning platform. That's the link. It's like Netflix for books, but you'll get the first week for free if you're registering. Second, if you already know what is domain-driven design, then I share the story of our company, how we use domain-driven design for 7 years. You can find that story as a chapter in the book called Domain-Driven Design: The First 15 Years. Actually, that's one you can get for free. If you follow the link, you just set your own price. If you want to work with me, check the careers we have at Do It International. And if I still didn't bore you to death, that's my Twitter. And now I will get to questions. Are you suggesting components are coupled when they maintain similar logical views? Where is the coupling? So if they contain the same business logic which produces those views, and those components have to change because for the same reason, then you have coupling. If accidentally, for example, you have two components producing the same view, or it's not really important to evolve them simultaneously, then they're not really coupled. So it really depends on the reasons for change. The second question is, how is the outbox pattern any different? What's to prevent the power outage from breaking the new flow? So once we get that approval from the database that transaction was committed, the data is there. The relay, which runs asynchronously, will pick that message up either now or even in an hour, but that event is still going to be published. Also, because we are writing those events into the same table, we can use the table's index, to check the order, in which order those events were written. Do we have any more questions? Come on, people, don't be shy. Okay, if you have any questions, I'm here. Thank you so much for coming.